Sorry about that. Leah was just causing some trouble there. It's way past her bedtime. So let's take that negative half off. I wanna eliminate that before we get going. Okay. So let's talk about this cos x and subtract 1 and then divide by x squared. So I'm gonna rewrite a bunch of these terms. We're gonna sort of use a shortcut here. We'll write a lot of them so we can sort of see what's going on. Okay. Dot. And this is that expression for cos x, right? This is that expression for cos x. And then I'm going to subtract 1. When I subtract 1, all that really does is it eliminates this one, right? And then I want to divide the whole thing by x squared. Divide the whole thing by x squared. So what's that going to give me? Well, it's going to reduce the degree of all of these top terms, right? So I'm going to have f of x equals, and we're going to reduce the degree here by 2, right? Because we'll have negative x squared over 2 factorial x squared. So that's just going to be negative a half, right? Which is what we really wanted. We sort of took a long way to get there, but now all these other terms are going to flow a lot faster, right? So if x to the 4th over 4 factorial times x squared, right, that's going to be x squared over 4 factorial. And then the next one's going to be x to the 4th over 6 factorial, and so on, right? Because each one, we're going to reduce this degree by 2. This degree by 2. So the general term is going to be something kind of simple, right? It's going to be negative 1 to the n plus 1, and then, because we want to start negative, and we're going to end up with x to the 2n over 2n plus 2 factorial. And you guys can sort of reason that out if you'd like. Okay, so let's talk about, oh boy. Never mind, sorry. It's my dad's birthday, and I thought my mom wanted me to call him now, but never mind. Neither here nor there. Anyway, let's talk about B. So use the Taylor series for f about x equals 0 in part A to determine whether f has a relative maximum, minimum, or neither at x equals 0. So if we're going to talk about f, let's talk about the first derivative. Okay. Well, we can see that if I were to take one derivative of this thing about 0, one derivative, let's think about what that would mean. One derivative of this guy, well, and evaluate at 0. So f prime of 0, right? Well, this first term is going to go away, so that's just 0. And then every subsequent term, right, we're going to have 2x over 4 factorial minus 4x cubed over 6 factorial plus dot. All of these guys have an x in them, right? So f prime of 0 is 0. Something I shared with, I think, both classes, maybe not, is that if they're asking you on one of these things to determine whether it has a relative max or min or neither, right, they're going to be asking you to apply the second derivative test. We should assume the first derivative test is probably going to yield 0, or else obviously it has neither, right? The first derivative isn't 0. It doesn't have a max or a min. So we should assume that we're probably going to have that. So this is good that we got that the first derivative is 0. What about f double prime? Well, this is the first derivative. And the second derivative of this thing would be, this guy would be 0, right? 0. This first term would be 2 over 4 factorial. Then I would get 12x squared over 6 factorial plus All these guys would have a 0, right? Because all of them have this x in there. So they would all be 0. They would all be 0 at 0. So this second derivative of 0 is really 1 over 12, right? It's really 2 over 4 times 3 times 2. That's how I got that, 1 over 12. So because this thing is therefore, the second derivative is positive and the first derivative is 0, it's concave up, we can say this is a relative min, right? So again, test-taking strategy, if they're asking you to find a min or a max of these guys, or whether there's a min or a max at a specific point, you should think, oh, I'm going to take the first derivative, it's going to be 0, and then I decide whether it's concave up or down. Okay, write the 5th degree Taylor polynomial for g. Oh, God, what's g? Oh, geez, that thing. For g about x equals 0. Okay, well, that looks scarier than it actually is. G is just 1 plus the integral 0 to x of f of t dt. Right? So it's really just asking, can we integrate f? We sure can, right? So we already have this expression for f down here, right? Here's my expression for f. And I just need to integrate it, right? So g is 1, g of x, sorry, is 1 plus the integral from 0 to x of f of t dt. Well, that's just integrating this, right? So I just want to integrate this thing that I'm going to now circle in blue. I want to integrate this, and it wants the 5th degree. That means we've got to go out till we have x to the 5th. So g is clearly 1 plus the integral of this thing. So what's the integral of the first term? Negative a half, that's just negative x over 2. What's the integral of the second term? Well, that would be, what are we going to get? We're going to get x cubed up here, and then I would need to throw another 3 in the bottom. So something like this. What's my next term? I would get an x to the 5th, so I would need to throw an extra 5 in the bottom. And if you take this derivative, you'll get this thing up here in blue, right? And dot, 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 but we don't actually need that. We don't need the dot, 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 because it just asks for the 5th degree one. So that's it. That's the answer to C. And then D, we're finally getting to our error piece. I hope this other thing was somewhat illuminating. Sorry for the break in the middle. Right, so I might have edited that break out, so if you have no idea what I'm talking about, that's great. So the Taylor series for G about x equals 0, evaluated at x equals 1, is an alternating series with individual terms that decrease in absolute value to 0. Okay. Use the 3rd degree Taylor polynomial for g about x equals 0 to estimate the value of g of 1. Oh boy. Explain why this estimate differs from the actual value of g of 1 by less than 1 over 6 factorial. Okay. So, estimate g of 1, right? This is, again, the Taylor series is some approximation for a polynomial, or for a function, right? So g of 1, we can just say, oh, well, that's 1 minus a half plus 1 over 3 times 4 factorial minus 1 over 5 times 6 factorial, right? We're just plugging 1 into this, right? You can take, oops, we only want the 3rd degree one, so we only need these guys. You can take my word for it. This is a half minus, or plus, sorry, plus, what is that thing? 4 times 3 times 2, 24 times 3, 72 maybe? 1 over 72, so this is 37 over 72. Great number. Okay. And that's the first part of this. And then let's talk about our error bound. Okay? So we know that in an alternating series, right, from what we saw above, is that the greatest that this difference can be, right, the most that we're actually off by, right, that the difference between g of 1 and this partial sum. Remember, this is what, like the 3rd partial sum here, right? That this difference here, this difference that we're off, has to be less than, right? Because this is the actual value, this is the estimated value, has to be less than the next term. The next term, right? That's what we showed way up here, right? That we said, oh, my actual remainder here, the difference between my partial sum and my actual sum is less than the next term for alternating series, right? So we're saying that the difference between actual and my partial sum is less than the next term. And what is the next term? The next term is 1 over 5 times 6 factorial. That's the next term here, right? If I plug in 1 for x, I get 1 over 5 times 6 factorial. Okay? And we agree, right, that this thing is certainly less than 1 over 6 factorial, right? We multiplied the bottom by 5. So we've shown, right, that the error bound is actually less than 5 times 6 factorial, which is certainly less than 1 over 6 factorial. So I hope this made some sense. I'm going to send out another video from the College Board also that will hopefully help you with alternating series error.